All right, more of the output. The output consists of a bunch of objects, and the loop invariant will say, oh, that's funny. I just fixed those, but I fixed them in a kind of a funny way. That's okay. The output, the loop invariant says I've produced the first I of them, right? Or produced some I of them. Maybe you're doing them in a different order. And so what do you do in the step? Obviously, you produce the next one. And what is our measure of progress? How many you've done? And how do we get our, what's our exit condition? Is you produce them all, and clearly then we have our post condition, right? Everybody good? So again, let's go back to sorting. Our input's a bunch of numbers to sort, and the output is those numbers sorted. So the loop invariant is going to say that we have produced the first bit of the output. And what is that going to tell us? If this is actually the output, it's going to tell us these numbers are sorted, and it's going to tell us what's the relationship between these numbers and these numbers. These numbers are smaller, right? Because that tells us something else about the fact that these are the beginning of the solution of the entire, right? So that gives us what we're looking for to continue. And how do we continue? Well, maybe we need some extra information which tells us which ones we've done already. We find the smallest, and we put it where it belongs. Right? Everybody good? All right. So I don't know if it was in your tutorial or in the other tutorial, but one of the tutorials we covered cake cutting. In fact, we did it in both tutorials. Right? And the loop invariant, I realized at some point the loop invariant was something different than, it wasn't really more of the input, it wasn't really more of the output, it was somehow something different. So let's kind of think about what it was. It said we have a bunch of inputs and we have a bunch of outputs. And one of the words I changed the word here to a set of inputs. From before I said it was an array of inputs, which implied an order. And here it's a set of inputs, so there's not necessarily an order on them. We can consider them in any order we want. And the loop invariant is going to say, well, I've kind of handled some of the input, and I've produced some of the output. And maybe they're corresponding, or maybe they're not corresponding, right? But, right, these might be the people, and some of the people I've given cake to, right? So this is the output, what cake they have, right? And what do we know? We know that with respect to the input that we haven't done yet, we still have the precondition, right? We still say that the people who haven't been given cake, there's enough cake out there that they're sufficiently, right, that they have, that it's worth I over n, right? And then what do we know about the guys down here? The loop invariant is also going to say we've gotten the post condition for the ones we produced already, right? These guys here have enough cake to be happy, right? Does that make sense? I'm just saying we can open up the loop invariant to be a little bit broader than I was thinking before. Right? Are you guys good? All I know about this is the example of the cake cutting, right? So, but you can imagine that there are things like this, right? Everybody see cake cutting here, right? These people are happy. These people still have the precondition, right? This cake has been produced, and it meets the postcondition. All right. So here's an example that I think is fantastic. I got this at some math conference. We have an infinite number of blocks that we're able to stack up. And each block is 2 inches long. We don't care how wide or how high it is, right? And the goal is to stack them up so that the top, and you can shift them. The goal is how far can you get the top block shifted from the bottom block, right? And of course, the requirement is that it doesn't fall, right? And it's not just that it falls here, right? Each block, no blocks are attached, so it could really crumble at any spot along the way, right? So here's the question. Maybe we can get people's intuition here. How far can this top block shift, right? Can it shift past the bottom block? How many people think you can shift it past the bottom block? How many people think, no, if it gets to the bottom past, it's going to fall over? How many people really don't have any idea? All right, that's reasonable. Somebody in the last class just seemed to know the answer, and I don't know if he knew it from somewhere else or whether he was just... Anyway, let me prove to you that it can't go arbitrarily out. All right? Here's a proof. So if we're doing more of the output, it says, well, we've produced some of it, and it hasn't fallen over yet. And we've shifted. If you want to, the question is, can you shift arbitrarily far out? Can you shift this far out, right? Well, once you've shifted this far out, if you want to go further, right? If you want to keep adding blocks on top, well, let's not even try to shift further. But you put enough blocks on there, right? It's going to fall over, right? So how can you possibly go much further out? Right? Everybody buy this as a proof? Everybody agree that we can't go very far out? All right. So now, that was great, but I'm going to now prove to you that you can go arbitrarily far out. All right? And first we might say, well, what was wrong with the proof that I just gave you? Right? And the proof I gave you implied that certainly if you built this, if that's how you started, then you can't go much further out without it falling, right? So what we're going to change is you have to know ahead of time how far out you want to go, how high you want to go. You have to plan ahead. And how you start building at the beginning will depend on how far you want to go, all right? And so working towards that, we're going to turn things around. We're going to still do more of the output, but we're going to build it from the top, right? So our loop invariant will be that we've stacked something up like this already, and that it doesn't fall over, and we've made some progress. It's shifted out so much. And when it doesn't fall over, I'm saying more than that, the whole thing. But as I said, each block is stable. Right? Now, I have to warn you, the way we're gonna build it, you don't want to blow at all, right? Keep the wind down because it's teetering there. Okay, we're going to need extra information. We're going to need to know where the center of mass is. People have done enough physics to know there's some point. This is the point where I could balance it all on my finger if I was really a balancer, right? And one thing that should be obvious to everybody is the center of mass can't be here, right? Center of mass has to be under a block, or else it would topple over. And we know how far we've shifted, all right? And so now how are we going to take a step? Can we put a block on top, right? Can we do that? No. Obviously, it'll fall over, right? So instead, we're going to slip a block underneath, right? And so can we put the block there? No, it has to be under the center of mass or it'll fall over, right? So do we put the block there? Why? Because we need to make some progress. So where are we going to put it? I'm going to live dangerously. And we're going to put it so that the center of mass is just teetering on the edge. Right? Now, if you wanted to, the whole thing would go through just as well if we cut the distance in half. Right? So we wouldn't be quite so greedy. But here, let's go for the full. Right? Everybody good? So, And now, to maintain our loop invariant, we have to calculate the new center of mass, right? And I know, well, I certainly know that I didn't remember the equation. I probably learned it in physics. But you go, what do you do now? You Google it. You don't have to go to the library, right? So you Google it. And this is what happens here. Suppose you have two masses, and you know how heavy they are, and you know their center of masses. Their masses, right, and their center of masses. And how are we going to measure where their center of mass is we're going to have some definition of 0, and we're going to know this distance and this distance, right? But where your definition of 0 is, that turns out it doesn't matter, right? Everybody good? And then what is the formula? It's going to be, we want to take the average of this R and this R, right? But it's a weighted average. You can see here we're weighting it by what percentage of the mass is in M2 is how much R2 gets, and how much of the masses in M1 gets, right? So if one of these masses was 0, then it would be the other. And if the masses were equal, right, then it would be the average. All right, so now let's do it. Let's calculate what our masses are. Well, the mass of the green block is just one block, so let's call it 1. The mass of the blue block, as 1 unit, well, we haven't said how many there are there, but let's call them, let's say that this is our ith block, so the number above us is I minus 1, right? So we have our masses. So now let's figure out where our center of masses is, all right? We know the center of mass of the blue block is right there. That's what we said. And we can set our 0 measure anywhere we want, right? So just to make the math easy, let's call the center of mass of the blue 0, right? And then what's the center of the mass of the green? Well, it's in the middle of the block of the green. So what's this distance? It's going to be 1, because the block has this length 2, which is why I set it to be 2. Make our math easy. Everybody good with this? And so then we calculate out the center of mass, and it turns out that the center of mass comes out to be exactly 1 over I. All right? So what we're saying is, here's our old center of mass, here's our new center of mass, and it's shifted by 1 over I distance. Right? Everybody buy that? So now, let's keep going. Where do we put our new block? Right? We want to calculate the shifted distance. Where do we put our new block, our I plus first block? We shift it by an extra 1 over I. Right? So now we can go back and calculate what our total shifts are. Right? And that tells us, right, that shift is 1 over I, and our first shift is going to be 1, right, because the block is of size 2, right, 1 over 1. Right, everybody get that? So this shift is 1, this shift is a half, this shift is a third, this shift is a fourth, right? You guys look so asleep. You should be excited. This is a fun problem, right? If you're understanding it, you should be a little bit more enthusiastic, right? So what's the total shift? Well, it's the sum, right? It's 1 plus a half plus a third plus a fourth plus a fifth plus a sixth. Now, this is a very famous sum. People know about this sum? It's called the harmonic sum. I don't know its relation to harmonies. I don't know why it's called the harmonic sum. But one of the reasons it's famous is that if the terms, let's talk about sums again, right? Here we're adding 1 plus a half plus a third plus a fourth, right, up to 1 over n. And I told you that there were two types of sums that we were considering, right? Geometric sums and arithmetic sums, right? And with the arithmetic sums, remember usually the sums are getting bigger, right? 1 plus 1 squared plus 2 squared plus 3 squared up to n squared, right? And then I said, well, the terms aren't growing so fast, so the sum will be within a constant of the biggest guy times the number of terms, right? So the sum becomes n times n squared, right? Now, if they're shrinking, then we could say it's the biggest term times the number of terms, right? So then it would be order n, right? And the truth is, if these shrunk just a little bit slower, right? These are shrinking fast. They're shrinking too fast to give you this. If they were shrinking a little bit slower, then you would get this, right? The other option is, suppose we're going 1 plus 2 to the 1 plus 2 to the 2 plus 2 to the 4 up to 2 to the n, right? These are growing so fast that we're dominated by this, right? And so the whole sum is this. Now, similarly, if these were shrinking just a little bit faster, right? Certainly if they were going down 1 over 2 to the I. But if they were just shrinking a little bit faster, if they were shrinking 1 over 3 squared, for example, right? Then the sum would be dominated by the biggest guy, and you would get a constant, right? But this sum is just teetering between those, right? And it turns out that it adds up to the natural logarithm of n. And if you want to get some intuition of that, try it yourself. The first term is about 1. And the next 2 terms is about 1. And the next 4 terms is about 1. And the next 8 terms is about 1. And so you can, when I say about 1, I mean it's going to be bounded between, right? This is less than 1 and bigger than a half, right? Each one's going to be less than 1 and bigger than a half, right? And so that's how you can say this is between log n base 2 and half log n base 2. Yeah? Well, my little argument there proved that it's between log n and a half log n, right? If you do these blocks. And the actual answer is ln n, which is in between, right? And one way you might, I don't know if you remember the integral of log n, right? We could do calculus and it's ln n. Right? Right, everybody good? In fact, this is really close. I think it's accurate certainly within 1. It's called the yeah. All right. So anyway, what does that mean? That means you can shift as far as you want, right? And remember, see here I say that it gets closer and closer. So you have to decide how far you want to shift, right? And this part is fixed, but this part isn't fixed. So you decide how far you want to shift, and then the number of blocks you need is exponential in that distance, right? So, and you might, if you stand on your head, then that's an exponential curve, right? And so you can keep stacking. Everybody, that's kind of fun, right? And then last year, I've been doing these slides for a number of years, and last year somebody sent me this link, and if you follow the link, you get this picture, which is, you see it's these men, each man is holding the head of the man before him, and they're doing that. And it doesn't say it, it's just the statue. But you kind of figure it's doing something like we're doing, right? So that's pretty cool.